Hello everyone. In this video, I wanted to address a common issue that I'm seeing with the labs from week one. So first, what we're going to do is configure our emulator driver. So this is the Slick 500 DH45 emulator driver. I'll go ahead and choose Add New, and I'll just call this Emulate. Really, the name doesn't matter, and if you're using the app stream, it's going to delete it once you close the session. So you'll have to do this multiple times if you're using the emulator with AppStream. So we'll just give a quick station name, just call it my laptop. So now we can see that our emulator driver is running. Everything looks good here. So I'll go ahead and close that out. Another thing I want to note is that I'm running the emulator in the background. So we just want to make sure that's running. You shouldn't have to do much to it other than launch it. But I'll show you some ways that you can check to verify that it's running. So next I'm going to open a new project. We'll choose the RsLogix 1100 Series B PLC. This generally works better with the emulator than the Slick 505s that we use in class. So just know if you use AppStream, you're doing remote access, make sure you choose the RsLogix 1100 instead of the Slick 505. So I'll choose the driver that I just created, processor node of 1. This really just has to be different than whatever your station node number is. So the station node that I configured in RsLogix was station node 4. So I'm going to choose 1 for the processor node, click OK. So I have a new project. The issue that I want to cover here is the different types of coils that are available in RsLogix 500. So I'll just create some quick rungs here on my default ladder. So I'll use an open contact with a standard OTE coil. So OTE stands for output to energize. If you hover over the instruction, it gives you just a brief description of what that symbol is. But the shorthand for that symbol is OTE. Next, I'm going to add a open contact to my next rung. And this is going to be another type of coil that is OTL, and OTL stands for output to latch. This is a latching type of coil. And then lastly, we're going to use another open contact, and we'll add a OTU, and OTU is output to unlatch. So I'll just create a quick program here, show you the different ways that these coils function, and hopefully by the end of the video you'll understand why using either the latch or unlatch coils would have been incorrect in the week 1 labs. Okay, so I'm just going to use the B3 addresses here. These are internal addresses, internal bits that you can use for testing. So I'm just going to do input 1 here, and then we'll call this bit 0. And on this side, I'm going to use the next word. So you can see on the input, I have B30. On this one, I'm going to use the next word, which is B31. And then to reference the individual bit, I'll choose the first one available. And we'll call this output 1. And we'll just call this out 0. Next, I'll choose the next address in the B30 word, and that's going to be bit 1. We'll call this input 2 and bit 1. And then for this one, we're going to use the same word that we used for the previous output, and I'll just use the next available bit for that one, and we'll call this latch output 1, and we'll call this out 1. Okay, and then finally, we're going to use a different input bit for the next rung, but on the output to unlatch, we're going to use the same bit that we used for the output to latch, and I'll show you why once we download the program, and hopefully you'll see how this functions and how it differs from the output to energize. So on this one, I'll just choose the next available word, which is B30/2. And this is going to be input 3, and we'll call this bit 2. Okay, next we're going to address this unlatch bit with the same address that we used on the previous rung, which is B31/1. Okay, so now we have a pair of a latch output paired with an unlatch output. All right, so next we want to verify our project, and you'll see that my toolbar is missing some of the instructions. I don't have the verify. So to fix this, you just go to Window, Arrange, and click on Default Toolbars, and that will bring all of the default functions that are normally available in the project. For some reason with AWS AppStream, a lot of times when you open the project, these are missing, so you have to do that Windows and set the default step. Okay, so now we'll click on the first rung and we'll verify this code. Everything looks good. I'm going to save my project and we'll just call this output test, and I'll save it in the temporary files, and I'm saving it here so that it's easy to transfer. The temporary files folder is available in AWS AppStream and allows you to easily transfer files from the temporary files folder to your PC. All right, next I'm going to choose the download option from the drop-down here. So we'll click download, and we don't need a revision note. It's just asking me if I'm sure I want to download, so I click yes, and then it will ask me if I want to go online. You can see it's currently in remote program, so we want this in run mode so that we can test the bits. All right, so now we have 3 rungs. One is energizing a OTE coil. The next one is energizing a OTL, output to latch coil. And lastly, we're de-energizing the same output to latch coil from above. All right, so one thing we want to verify is just that our emulator is running. We already know it is because we have green statuses, but another way you can verify is by going to the emulator, and you can see here I have my output test project open and it's currently running. There's really nothing you have to do with the emulator other than just make sure the window's open. You can see in the bottom corner it says that it's currently in run mode. I can actually halt my program, so if I do the HLT halt, it will stop the program. You can see on the left hand side it went from running to remote program, and it's now blue. I can also do test, so this will test incremental executions, so you can step through executions rather than the nature of a PLC is that it will continuously execute the rungs just kind of indefinitely. It's basically an endless while loop that's looking at the run status of the PLC. So while the PLC is running, it will continuously execute the code. You can also do a one shot, so that will like trigger one execution, kind of similar to this test. So we'll keep this in run mode for this test, and we'll just run through this logic. So one way you can test bits is by toggling it directly from the rung. You can also open the data table. So the data table will have both words that we're using in this project. We have B30, and then we have the individual bits of that word. So 16 bits for each word, and they all start at 0 going to 15. You can see B31 bit 0 on B31 is also energized, and that's because OTE will pass whatever value the inputs are providing. So if the input is true, then the output OTE is also going to be true. All right, so we'll go ahead and de-energize this bit, and then we'll see something interesting happen with the next one. Okay, now if I energize input 2, so bit 1 of B30 word, I'll go ahead and energize that, and we'll see that our OTL turns on. So you can see that it's green, and then you also see that the OTU turns on. So this is the biggest difference between OTE and OTL. So I'll go ahead and open my data table, and I'm going to turn off bit 1. But you'll notice that B31/1 is still on. So what this is it's a latching coil, meaning that it will, on a rising edge, so when this transitions from false to true, the output to latch will energize, and it will stay energized until it receives an unlatch command. So it receives an unlatch command using the OTU instruction, output to unlatch. These are always created in pairs, and you can run into issues if you create an output to latch and don't create an equivalent output to unlatch with the same pair and the same addressing. So these are always addressed together. You can see B31/1 is the same address as my output to unlatch, B31/1. All right, so to de-energize this coil, you issue a true command to the output to unlatch coil. So the way that we would do that is we would use bit 2. We would energize that. So on rising edge, meaning transition from false to true, this will unlatch and both coils go false. So that's our expected behavior, and that's the difference between the OTE, OTL, and OTU. So what I noticed with some of the lab submissions is that several of them had a rung that had an OTL instruction, and it had no OTU instruction to unlatch it. So what will happen when you test that is when you push your inputs on your workstations, it will turn on that output and will never become de-energized. So that light will stay on indefinitely until you issue an output to unlatch command. And in those particular labs, there wasn't an output to unlatch command, so that output would never actually get de-energized. The latching and unlatching are commonly used in motor controls where you have a separate start push button from your stop push button. So one will start the machine, start the motor with a latch, and then you will stop the machine or stop the motor with an unlatch. So that's a pretty common use case for the OTL and OTU. I would just advise to be careful when you're adding instructions, especially when you're working with real world inputs and outputs, as you can energize something indefinitely and not really see it clearly because it's just a simple letter inside of the coil. All right, thank you for watching, and I hope everyone is having a great start to this semester. And if you have any questions, you can always reach me via email, message me in Canvas. I usually respond within 24 hours. All right, appreciate you watching, and hope this helps.